Hello guys. Hello everyone. I hope you are not here to look at a piece of wood because I'm not gonna show a piece of wood. Rather, I'll be teaching you the basics of logarithm. Alright? So let's just start. I'll be starting with some prerequisites for this lesson, and there are only two prerequisites for this lesson. Let me just select the color and pencil. Alright, so the first prerequisite is exponents. Okay, I hope you all know this. Even if you don't, let me just briefly explain this. Let's say the notation we use is something like this. We call this as 2 raised to the power 3. That means nothing but multiplying 2, 2 and 2. I mean multiplying 3 2's together, that is nothing but 8. Similarly, if I say 2 raised to the power 2, that means we are multiplying 2 2's together, that is 4. Similarly, if I write 2 to the power 1, that means there is only one 2. And if I write 2 to the power 0, so the answer is 1, not 0. So to avoid confusion, I like to write this as, let's say, it's 2 to the power 3. That means I'm multiplying 1 with 3 2's. Alright, multiplying any number by 1 doesn't make any difference, so we again get 8. Similarly, 2 to the power 2 is 1 into 2 into 2, that is again 4. And 2 to the power 1 is 1 times 2, that is 2. And now you will see that why this interpretation is better, because now for 2 to the power 0, I am multiplying 1 with 0 2's, that is nothing but 1 itself. So yeah, that is the few important parts of exponents which we'll be needing in the session later. Now let's move on to the next prerequisite. The second prerequisite is plotting. Well, nothing complex. You just need to know the 2D plotting. That too for points only, no lines on all. So let's say I have a point P. Let's say it has a value 3, 2, a pair of value 3, 2. Now, how do I plot it in the 2D plane? For that, I need a number line in one direction and another number line in the other perpendicular direction. Just for the sake of convenience, we write this as x direction and this as y direction. And this is our origin, that means the value is 0 here. Now, similar to the number lines, we assign values like 1, 2, 3, 4, 5, depending on our requirement. And same for y-axis, 1, 2, 3, 4. And now, for let's say here I have x equals to 3. So for x equal to 3, if I draw a line like this, for any point in this line, you will see that the x value is 3 only. So this is the line for x equal to 3. Now similarly, our y value is 2. Okay, I forgot to tell it that we can write this as p xy. That means the value of x is this and value of y is this. You can always take it the other way around, or anything you want. You don't want x, y, you can do a, b, or anything. That's just the convention. So our y is 2. So for 2 we have this line. Now everywhere in this line the y value is 2 only. Now you can see there is a point where these two lines intersects here. Here the x is 3 and y is 2, and only one point exists in the entire plane here for which the x is 3 and y is 2, and that is our point P 3, 2. Well, that's the basic of plotting. Now let's move on to the real deal. Let's say you are asked that what is 2 raised to the power 2, or say 2 raised to the power 3. Okay, this is a question of exponents, and that means 2 raised to the power 3 means 2 times 2 times 2, that is 8, right? Now let's say I ask the question in a different way. Let's say if I ask you 2 raised to the power of what gives 8. Now looking at this previous question, you can easily interpret that the answer should be 3, right? So what we did here is the logarithm. What we did here, in logarithmic sense, we write this as log of 8 with base 2 is equal to 3. That means that when we raise 2 to the power 3, we get 8, right? I mean, that's corresponding to 2 to the power 3 equals to 8. So this is the logarithmic representation. That's nothing but a mathematical tool which looks very simple but is very useful. I'll tell you why later in this video. So let me ask you a few questions. You will pause the video after that and try to solve it by yourself. These are very basic questions, so I don't think you will need any time. The first one is so just pause this video and try to think over the answer. I hope you all get the right answer. Okay, the answers are log of 16 base 2 is 4 because 2 raised to the power 4 is 16. Similarly, log of 27 base 3 is 3 because 3 raised to the power 3 is 27. And log of 1 base 1 is actually, you will say that that's just 1 because like log equal to 1 because 1 to the power 1 is 1, but 1 to the power 2 is also 1. 1 to the power 3 is also 1. So log of 1 base 1 is not just a number but a set of numbers, right? Log 1 base 1 will be the whole real number, like minus infinity to infinity. All the powers of 1 gives us 1. So our real answer should be this. This is also an answer, but this is just part of the answer. The whole answer, the whole set of answers are these. Okay. Well, there are a lot of dangerous questions as well, but let me write some simple looking dangerous questions. You can try it later after completing this video. So the questions are, let me write dangerous questions. Okay, so the dangerous questions are the dangerous. So the dangerous question number 1 is, what is log of 1 with base 2. Dangerous question number 2. What is log of root 2 with base 2? Dangerous question number 3 is what is log of 0 base 2? Alright, you can try this after completing this lesson. Right now, let's move on to the next part. Now we are familiar with the integral powers of any number, like 2 to the power 2, 2 to the power 4. Now let me introduce you 2 to the power 0.5, I mean the decimal powers. So a very simple example, 2 raised to the power 0.5. What is that? Like, if you try to understand it intuitively, that what powers are, like 2 raised to the power 2 is 2 times 2. 2 raised to the power 3 is 2 times 2 times 2. What is 2 raised to the power 3? Like, is it like, is it like half of the 2? Like upper half, or maybe lower half, or maybe front half, or maybe back half? Well, all of these are wrong. 2 raised to the power 2 has some value. Well, I'll explain you in a other way. 2 raised to the power 0.5 has some value. What's that? I mean, you might be familiar with this irrational number under root 2. What's the value? That is something 1.414 dot dot dot. Yeah? Well, that's 2 raised to the power. Well, that's nothing but 2 raised to the power 0.5. 2 raised to the power 0.5 is root 2. Now, see, integral power are intuitive to understand. Like, you just multiply that number by itself some number of times. But when the powers are in fraction, it's quite less intuitive to think of. So, because there is no direct approach to calculate the value of fraction power, or what we call decimal power. So how we try to calculate the exact value? Let me give you an example. The same example, 2 raised to the power 0.5, right? That is 2 raised to the power 1 by 2. Let's say our number is a. Alright, so what does that mean? That means 2 is equal to a square, right? So our target is to find the number a such that the square of that number equals to 2. For that, we will start with a guess, right? Let's say our a is 1. What is 1 square? 1 square is just 1. Well, it's far less than 2, right? So let's change our number, okay? Now, next one, we have 2. Let's say our a is 2. What is 2 square? 2 square is 4. Well, that's more than what we are expecting. Well, that's more than what we want. So we need to increase the precision. How? Let's move on to the next decimal. Let's say now that I guess that my a can be somewhere near 1.4. What's the square of 1.4? It is 1.96. Well, it's almost close to 2, but not exactly 2. Okay, let's increase the value by one step. That's 1.5. What's the square of 1.5? That is 2.25. Well, that's greater than 2. Won't work. Let's increase the precision even more. Let's move on to another decimal digit. Now let's say we take a as 1.45. Square of that will be 2.5. something which is obviously greater than 2, so it won't work. Let's decrease that. What about 1.44? Square of that will again be more than 2 point again something something. What about 1.41? Square of that gives 1.989 dot dot dot, very close to 2. What about 1.414? That is around 1.99 something, very close to 2. Well, if I keep on increasing the precision, this number will tend to 2 more and more and more. So up to this decimal number, my 2 to the power 0.5 is almost equal to 1.414. So that's how we find the fraction power of any number. Well, for 2 to the power 0.5 it looks quite easy, but for bigger numbers, for more smaller fractions, sometimes it gets very hectic. So we don't calculate it by hand. We use computational method. One of those method is what we called Newton's method. Okay. What it does is that we define a function. Let's say we are asked that what is 2 to the power 1 by 2. So we say that 2 to the power 1 by 2 is a. That gives again a square equal to 2. Now we define a function f of x, which is x square minus 2, right? And if x tends to a, that means x square will tend to a square, that is 2. So our function fx will tend to 0. That's what we use in our programming. For that, we define an iteration formula. Let's say that formula is ix. So here we first start with a guess value of x, say x0. We put that x0 here and it gives us x1, and we test it on our fx, and if our fx goes to 0, then we stop and say x1 is our answer. Otherwise, we again put x1 to ix, which returns us another x, that is x2. Now again we put this on fx and check if it is close to 0, and keep on this iteration until we come up to an acceptable value. Well, this Newton's method itself is a big topic to discuss, so I'll stop it here. I hope you understood that why calculating fraction power is very inefficient. So I explained all this just to make sure that you know that fraction power exists and has some values. Alright? So now let's move on to our next topic, which is some properties of logarithm, some basic properties of logarithm which will be useful throughout your journey of logarithm. So let me first again write the structure of log, that is log a base b equals to c. Let's say this is the log structure. Okay, so let's prove our first property. So we know that log a base b is c. What that means is b to the power c is a. If I substitute this c value on this, and what will I get? I'll get b to the power log a base b is equal to a, right? I mean, what I did was just to substitute the result in the previous equation, and initially it will look very simple, but it's a very useful formula. All right, let me just highlight this. Okay, now let's move on to the next property. Now let's say we have log of a raised to the power n, it's inside, and base b, and let's say that is equal to c. So what is this? It means b raised to the power c is a raised to the power n, and let's move the n to the other side. That gives b raised to the power c by n is a. Now again, what logarithmic representation says for this equation is that log of a with base b is c by n. That is, log a raised to the power n with base b is n times log a base b. Again, a simple looking formula, but really very important in the world of logarithm. Okay, let's move to the next property. Now let's say we have log of a number which is multiplication of a1 times a2 with base b, and let's say that's equal to c. That means b raised to the power c is a1 times a2, and let's use the property here. B raised to the power log a with base b is a. That means if I substitute this a with a1, what I'll get is that b raised to the power log a1 base b is a1, right? So we can substitute a1 and a2 from there. Like, we can use that formula to rewrite the a1 and a2 like this, equals to b raised to the power log a1 base b times b raised to the power log a2 times b. And powers add up, so what we will get is b raised to the power log a1 base b plus log a2 base b, and in the left hand side we have b raised to the power c, that is nothing but b raised to the power log a1 a2 base b. Well, since the base is same, that's b is same, so I can just remove the base and compare the powers. So the powers are log a1 a2 base b is equal to log a1 base b plus log a2 base b. Well, let me write it here. You can already see what's happening here. Log a1 base b plus log a2 base b is equal to log a1 times a2 base b. Look at this. Addition of log multiplies the value inside. Cool, right? Well, let's move on to the next formula, next property. Now let's write log of a number which is a1 divided by a2 and base b, and let's equate it to c. And obviously a2 cannot be 0, right? You know that finite number thing, right? Otherwise it will be infinite. So we can write b raised to the power c is a1 by a2, and again we substitute a1 and a2 by b raised to the power log a1 base b divided by b raised to the power log a2 base b. And in division, power gets subtracted. So we can write this as b raised to the power log a1 base b minus log a2 base b. And on the left hand side, this is nothing but b raised to the power log a1 by a2 base b. So again we can compare the power and come up to the result, which I am writing directly, that is log a1 base b minus log a2 base b is equal to log of a1 by a2 base b. Well, that's similar result as the previous one, but I had to prove it because it is division, not multiplication. Alright, so these are the 4 useful results of logarithm. Any further definition, any further properties of logs you will come up to, you will definitely use only these results to prove them. Okay, now you know what log is and what are some properties of log. Now let's come to the application part, like why this is important. So let me explain you why this is important. So for that I will again use an example, and now it's time to use the second prerequisite I mentioned, that is plotting. So let's say I have a few points p and x comma y that are, the first point is 1 comma 10, let's say. The second point is say 2 comma 100, and the third point, let it be 3 comma 1000. Okay, and let's just close it. So here 1, 2 and 3, 1, 2 and 3 are the x values, and 10, 100 and 1000 are the y values. So first let me try to plot it in the traditional linear way. Okay, for that I need a axis here and another axis here. So again let's assign the name. This is y-axis and this is x-axis. Now since in the x direction I see not much, now since in the x direction I don't need much change, so I can broaden the scale. Okay, first let's take this as 0, and now I can broaden the scale. So I take 1 here, then 2 must be here and 3 must be here. Similarly here it will be 4. Now for y, now you can see what the problem is, that I have to plot the 10, the 100 and the 1000, all 3, but I don't have much space here. So still let me try to just plot it. Let's say this is 100, this is 200, this is 300, this is 400, this is 500. Will we reach to 1000? 6, 7, 8, 9. It will be difficult to reach 1000. So let's just say that dot 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 dot, and here it is 1000. Okay, see, we are already here. We are already using those methods to shrink the graph. So let's start plotting it. The p1, okay, that's 1 comma 10. 1 is here, and 10 must be 1/10 of the distance from 0 to 100, right? So again I have to guess. You see the problem, right? So let's say this is the 1/10 of this direction. So this is our point p1. Now p2 corresponding to 2, and y equals to 100. This one is good for this because the order of our y is in hundreds. So p2 is quite easy to find. Now what about p3? Let's draw this line for x equal to 3 and for y equal to 1000. Damn. Alright, so this is our point P3. Now I think you almost understood what the problem is. Like, if we have a set of points where one value is changing very fast, like just for 1 it was 10, for 2 it became 100, for 3 it became 1000, and let's say for 4 it becomes 10,000. For P4 we'll have to go very high, right? So you see what the problem is? You understood the problem? Now let me show you the solution. Again, I'll be using the same x-axis because we don't have any problem with x. And here is the vertical axis, y. And now, instead of y, I'm gonna put log y here with base 10. And x should be here, right? Okay, wait, you will just see. X is 1. I think you people already guessed what is gonna happen. 2, 3, 4. Now this is 1, this is 2, this is 3, this is 4. I'll explain it just a moment. So what I did is, here it is 1. Okay, what 1 means, like log y base 10 equal to 1. What will like when log y base 10 is equal to 1, when y is 10, that means this one is corresponding to our this y value. Similarly, when is log y base 10 equal to 2? When y is 10 raised to the power 2, that is 100. That means this corresponds to our y value 100. Similarly, when log y base 10 is equal to 3, when y is 10 to the power 3, that is 10,000, that means this 3 is corresponding to our y value 1000. So we can plot this easily, like our P1 in this case will be this, and again P2 will be this, and P3 will be this. In addition, if we had another point P4, which is for x equal to 4 and y equal to 10,000, that means log y equal to 4 for base 10, we could have also plotted it just here, P4. You see how easy it became to plot? Like earlier the graph was diverging like very much, and now we converted it into a linear and simpler graph where I can plot for y equals to 10 to y equals to 1000 in a count of 4. You see what happened? So that is the power of logarithm. Okay. So again, what is log of 1 base 10? That's 0. What is log of 10 base 10? 1. What is log of 100 base 10? 2. Similarly, what is log of 1, 0, 0, 0, 0, maybe 18 times 0 with base 10? That is just 18. You see, if we had to write if we had to write the number, the full number, it would have been a very difficult task. Not impossible, but a very long task. but in terms of logarithm it is just a 2-digit number. So in logarithmic scale, from 0 to 18, we can cover the linear scale of 1 to 1 0 0 0 0 0 0. Let's just write this so that you can understand. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18. Wow. So this much number is covered in between 0 to 18 only. You see the power of log? Okay, do you need more? And in addition, the smaller values of log, let's say that is log of 1 is 0 and log of 10 is 1. So in the first one unit it covered 10 linear numbers, right? 10 linear units or whatever. Let's say 10 numbers. Now what about log of 100? That is 2. And what about log of 1000? That is 3. So in this time, again the step is again 1 only, but in the linear term there are around 900 numbers it covered. For smaller number it is more precise, and for larger number it converges, right? Well, that is very useful when we face datas like this, where in smaller terms we need some precision. Say for 1 I have 10 11 12 20 50 100, and then it goes on increasing 1000 10,000 80,000, so on. Now let me tell you where in the world do we use these logs. Well, obviously in mathematics we do use, but where in real life? The first point is to study a physical quantity very fast. Alright, so the examples are like the uses are, say this use, we use logarithmic scales to measure the intensity of earthquake, right? Earthquakes, the intensities, you see that you often see in news that today we had 6 magnitude earthquake, today we had 7 magnitude earthquake, today we had 5.5 magnitude earthquake. So these quantities are in logarithmic scale. What that means, that if there was an earthquake of magnitude 5 and there was an earthquake of magnitude 6 and there was an earthquake of magnitude 7, so obviously 6 is greater than 5. That means the earthquake for this intensity is much larger. But you know, in logarithmic scale, I just explained that how moving forward the steps for the linear scale increases dramatically. Like for the first step it's just 10, but in third step it became 900 numbers. So from 5 to 6 the change in intensity is not similar to the 6 to 7 change in intensity. So if 6 is a few times greater than 5, 7 is lot more greater than 6, and the ratio is not same. Alright, similarly the sound, our ears perceive sound logarithmically. Okay, let me write it. Ears perceive sound logarithmically. Well, why? I am keeping this as a task for you to research. Okay. Research means researching throughout the internet. I mean, yeah, you can use any ChatGPT or anything else, but I'll suggest you to research throughout the internet, look for some websites and read some articles on that, so you get a clearer understanding. And the more effort you put to understand something, the harder it gets to forget that thing. Yeah, it's right. So try to find that out. Another example is pH scale. Yeah, that pH scale, we use the litmus paper and then match the color, and we get the pH values to find if the thing is acidic or basic or neutral. That scale is also logarithmic. Another place where it is widely used is in astronomy. You see, in astronomy, we study the celestial objects which are far, far away from us, like maybe a planet, like say Saturn is some distance, some n distance away from us, and another planet that is n to the power 35 units of distance away from us. So you see the drastic change in the distance. That's why we use logarithmic scale in astronomy. And there is one more thing I want to say. Well, there are a lot of other things, a lot of other places where it is very important. So I'm not gonna make this video any longer. So before ending this, let me tell you one more thing. There's a special number E called Euler's number. And when we write log with base E, we denote it with ln. That is the special notation of log with base E. And what is so special with E is that all the natural processes like radioactive decay, I mean, wherever the rate of expansion or reduction is directly proportional to the value itself, that is, we describe rate by derivatives. Let's say our function f df of x by dx is proportional to function of x itself with some constant c. In these kind of scenarios, we use the natural log, that is ln. Yeah, it is called natural log. So maybe in another video I'll explain why this ln thing is very important to us, and I will also show you a few of examples, or maybe I'll derive a few properties which are very interesting, and once you understand, it will be hard to forget, obviously. So okay, let's keep that fun for the other video. And now, ending this lecture, I will be uploading this note in PDF form and the solution of the questions I asked as well. Alright. So now you understood that log is not a piece of wood, right? Alright, bye.